There we go. Se conviene con la luce, forse sì. Okay, so today is the last one. So it's not going to be maybe very long. So maybe we will finish before because we are tired and with the mask talking is a bit heavy. Okay, so last time we were starting another topic which I will just touch on, of course, which is the topic associated with the fluctuations. Let's see if it focuses, which allows in statistical mechanics to go beyond what happens in the thermodynamical limit and in thermodynamical equilibrium. Of course, there are some tools in statistical mechanics that allows us, let me write something. Vediamo se si focalizza. Scusate. That allows, as I was saying, to go beyond these two approximations. So last time we were doing a sort of exercise, which was computing the probability that a certain region of a space, a certain volume V, which is a portion of a volume V0, is empty. Or another thing that we were computing was the possibility that if you have a box which is filled with a gas, and you ask yourself which is the probability that half of this box is empty and the other half is filled, then this probability scales as e to the minus n0, when n0 is the number of particles, which is of course a very large number. Okay? So if you have a situation like this, the box which is completely filled, and you go in this condition, you can estimate which is the probability for this process to happen. And basically it corresponds to a decrease of entropy, because from here from here to here, you have an increase of entropy which scales as the logarithm, the n0 times the logarithm of 2, which corresponds to the fact that the volume is doubled. Ma non sta focalizzando, non so per quale motivo. And now, so then if you go from here to here, it's just the opposite. You have a fluctuation, a very big fluctuation indeed, for which at some point the entropy, for some reason, decreases so much that is reduced by a factor of e to the minus n0, not 2. Of course, this could happen in principle. Okay. Now the question is, so it's a very improbable fluctuation, because the entropy, the fact that the entropy increases is just a statistical statement. It doesn't mean that it always increases as a function of time, monotonically. There could be fluctuation, of course. So now the question is, how probable is this fluctuation? Well, it's very improbable in the sense that the probability for this to happen, we said, is e to the minus n0 logarithm also. The probability. For this gas to occupy half of this volume. Okay, of course this probability is very, non so perché non sta focalizzando oggi, scusate, ma devo fare qualcosa. Ah, ecco, adesso si vede. And something which is associated with this probability is to have an estimate of the time you have to wait until this situation occurs. So which is the time you have to wait until this process will occur. Now, we can make a sort of estimate which is the typical time scale associated with the change of the position of the phase of the point in the phase space in my system. So remember that the phase space was indicated with gamma, if I remember correctly. So this was the phase space. And the point here is Q and P is a representative point, contains all the positions and all the momenta of all the particles. So it's just a point that is moving in the phase space. Now, which is the typical time scale associated with the dynamics, if you want, of the phase space? We can make this sort of back of the envelope calculation. Now, if you have a system with many particles that collide, there is a quantity that is called lambda, mean-free path. What is the mean-free path? Is the path on average that a particle does before colliding with another particle. Okay? And the mean-free path actually can be computed from a microscopic point of view by using this relation, 1 divided by n times sigma, where n is the density of the particles, whereas sigma is a cross-section. Cross-section associated with the scattering of particles. And another quantity that we can compute is v, which is the average velocity, which can be computed by using the by using the equipartition theorem. And so 1/2 mv squared is equal to 3/2 kbt, from which the velocity is 3 kbt divided by n. And n is a density, so could be of the order, or one can put also real numbers, as I did here in standard conditions. Let me see what I have here. I have computed this at 300 Kelvin and 1 atmosphere of pressure, but not so important to do it. And but sigma, let's take a scale of sigma of the order of 10 to minus 10 meters squared. So P 0 squared, which is pi. Suppose that R0 is an atomic scale, which is 10 to the minus 8 centimeters squared. Of course, here I'm considering a geometrical cross-section, which is pi R0 squared, and R0 is a scale of atomic physics, which is order of 10 to the minus 8 centimeters. And you get a cross-section, which is order of 3 times 10 to the minus 16 centimeters squared. The other number is, so this is the cross-section, this is the average velocity, and here I think I have computed it for a proton, for instance, and I get the number which is of the order of 10 to 5 centimeters per second. You can try to estimate by yourself numbers. And I think what is missing is n. And n at 300 Kelvin and 1 atmosphere, it is of the order of 10 to or 2 times 10 to the 19 divided by centimeter cubed. Okay, so now if you play with those numbers, you can get a time scale, tau, which can be obtained by using a velocity and a lambda. No? In particular, if I do lambda divided by the velocity, I get the time scale, lambda divided by the velocity, which is the time you need to wait for one particle to interact with another particle. No, it's the free particle with the velocity, and you get a number which is of the order of 10 to the minus 9 seconds. Okay, so this is the scale, if you want, that somehow fixes the velocity at which this point in the phase space moves. Now, the thing is that if you want to reach a condition in which your gas, initially uniformly distributed here, goes to this situation, well, you need to wait. You can think of the process like a sort of random process in which you get one step, which is one step in the sense that one cycle of collision provided by the time tau. So you have to impose that the number of steps that your point must do times 10 to the minus and 0, let me forget about the log of 2, which is not important, is equal to 1. Therefore, the number of steps is equal to 10 to n0, which is the number of steps the point in the phase space must do in order to reach the situation that we call it B. This is B and this is A. Time steps, well, this number of steps, so the time, the total time, T, I have to wait, is tau times this n step, which of course is 10 to the minus 9 seconds times 10 to n0. Now, of course, I can also make the calculation fully, but of course it's not important, but okay, let's do it. So this is e to, this number is e to 10 to 23. Questo non era 10 alla n0, so really it was e to that minus n0. So just a proportionality factor, but it was e, sorry. So this number is e to n0 and must be multiplied by e to the minus 9 log of 10. And therefore, it's equal 10 to 20, 23 seconds. So the fact that the time scale is so small is not important, because in any case, the process will be dominated by this very large number. Okay. Now, of course, this number here is completely no variation method, the last lecture. Now, of course, this number has no meaning in the sense that it's so large that I cannot even imagine. The age of the universe is of the order of 10 to the 16 seconds, and this number is completely out of our scale. Okay? So that means that in principle, such a fluctuation can occur, but the probability is so small and the time you need to wait is so large that we will never see something this to happen in reality. Okay, this fluctuation. Now let me go on. Questo magari lo facciamo dopo. And since we are trying to somehow provide some insights to what happens at the macroscopic scale from the microphysics, let's introduce another process, which is the process of diffusion. diffusion can actually be explained in terms of random walk. We see. What is this? Random walk and diffusion. What is the process of diffusion? Well, it can be associated, for instance, with the diffusion of heat. So if you have a material in which some part of the material is hotter than the rest of the material, you will have the diffusion of heat that at some point will make the temperature uniform in absence of any source, external source. And similarly, I don't know if you're mixing two types of molecules, you will see that, well, coffee, milk, for instance, now this is also a process of diffusion, if you want, in the sense that the system will become uniform on a certain time scale, and is, of course, an irreversible process. So now these processes of diffusion can be described microphysically in terms of random walk. What is a random walk? A random walk in one dimension is the following. Suppose that you have, let me see, something like this. So let me see one straight line. And suppose that I have a particle here at a certain time t equal to 0, for instance. And this particle, as due to the interaction with the other particles, these are what unique one-dimensional process, but can be extended to three-dimensional, of course, has a certain probability of going to the right or to the left. With probability in absence of any external driving force, 1/2. So 1/2 right, 1/2 left. This is the probability that the particle changes its position as due to the interaction. Okay, these are provided by the interaction with the other particle. Okay. So you start at a certain position and you move with probability 1/2, either to the left or to the right. Then you repeat it. So suppose that at the first step you go to the left, then here again you have a certain probability to go left, a certain probability to go right. Then you have another step again. And you ask yourself which is the distribution of, well, of particles, if you have many particles, or which is the probability to find this particle in a certain position in space. Okay. Now, from the point of view of intuition, you will realize that on average, this particle, since the probability to go left and right is the same, the average position which will be exactly the initial one, basically. But there is a certain probability that the particles has a let's say, finite shift with respect to the initial condition, and this is what we are going actually to estimate. Now, the process itself can be modeled as a sort of Monte Carlo simulation. I don't know if you have done Monte Carlo in some cases. But in our case, we are not going to do any calculation because we are going to use a result that we already had. We can just work in an empirical way. Now I will write this formula here, and we will see how to use it in this situation. This formula was obtained for the one-dimensional system of independent spin. That was our starting point. You know, we had a chain of spin, which could be up or down, and N was the imbalance between the spin up and the spin down. This was the distribution, which is a Gaussian distribution that we derived in that case. Okay, this was computed starting with the binomial coefficient. So then we did some assumption, etc. Okay. So basically, the system was this one, no? Non-interacting, non-interacting. Now, in this case, the imbalance is the most probable value of the imbalance is n equal to 0. N was the imbalance. But we have a sigma, so a standard deviation, which is n. So the sigma squared is n. Okay. And okay, this was obtained by just using the binomial coefficient. So we can do a similar thing here. Now, the only thing that we have to do is to associate this number and this number here in this interpretation to other two numbers. Now, n must be substituted by a position. In this case, we turn in x, which is the position of the particle. Whereas now, of course, this was an imbalance. The imbalance goes from 0 to n, which is the number of particles, where x clearly can be minus infinity to plus infinity. And of course, dimensionally, they are not the same, but we will correct the dimensions in a moment. Now, what is n? Here, n was the number of spins of the number of these independent particles. Whereas here can be interpreted as the number of time steps, if you want. So this was the first step, the initial position, when then we did a step here, etc. So instead of n, must be actually something which is proportional to the time, because what we are asking ourselves, which is the distribution that describes the position of the particle after a certain time t. Now, of course, this t must be, if I want to substitute here x squared, here those two numbers are not dimensional, no, they have no dimensions. And here, if I write e to the minus x squared, here is a length squared. And if I want to associate with n a time, I need to adjust dimensions. I need to introduce another quantity, which is d, where d is called the diffusion coefficient. And it has the dimension of a length squared divided by time, in such a way that the exponential has a dimensional number. So this is a length squared divided by time. Okay. So then actually, what I have here is a certain number that provides me a normalization that I will write in a moment, times e and t, et. Okay. So at the end, the distribution, since the process basically, instead of having n, here I have time, instead of having a small n, which is the imbalance, I have the position, but from the point of view of the calculation, it's just the same, because in that case, we were computing in how many ways, for instance, I can put a spin 1, 2, 3, spin up and the other down. Here is the same. So here is in how many after a certain time, which is the probability that I've done a certain number of steps to the right and a complementary number steps to the right. Okay, calculation is basically just the same. So there's no need to repeat it. Now the distribution Px, therefore, must be equal to a certain constant k, which is a normalization constant that we will derive in a moment. Then we have the exponential of minus x squared, and here we have td. In the original there was a 2. Now for reasons that will be clear later, we write 4. Of course, this is arbitrary in the sense that I can define the diffusion coefficient as I want. Okay? And in order to normalize, in the minus infinity plus infinity interval, then we get that P of x is actually equal to 1 divided by this 4 pi dt. The exponential of minus x squared divided by 4 times. Okay. So this is the final formula that can be derived by using just statistical argument, as in the case of speeds. And we see that there are two things that are important to observe. These are Gaussian, of course. Of x is the function of x is a Gaussian, which depends on time, of course. But the average value, so x average, is equal to 0, as I expect, in the sense that now, if instead of one particle I have, if instead of one experiment I do many experiments, there is a game also in television with this sort of random step, no? You have some parts here, and then we have some balls falling down here. Have you seen this game? Telescope. Okay. So then each time you have a collision with this ball, with this part, then the ball can go here or here, then here or here. And then at the end, you get a Gaussian distribution. Okay, it's a sum of random steps. This formula here. Okay. So the average position is 0, and as expected. So if I do the experiment many times, I can realize immediately that most of the particles would accumulate at x equal to 0. But what is important to observe is that the sigma, so which is sigma squared, which is x average squared minus x squared, and now this is equal to, by comparing with the sigma in the Gaussian, is twice the t. So the sigma of this Gaussian distribution is increasing in time. So it's proportional in particular to t. So this means that if I do x squared average in the square root, is the square root of t. Okay. And this is typical, this scaling is typical of diffusion processes. So how large the Gaussian is, so the sigma depends on time, and the sigma scales as the square root of time. Okay, so which in this case basically it corresponds to the fact that you are increasing, if you want, the number increasing the size of this box. No? Instead of looking at the distribution here, you will look at the distribution in a larger box, which is like making more time steps. Okay. So in this respect, statistical mechanics provides a way to compute the distribution of particles in such a system, for instance, and it provides all the quantities that we need, in particular the average value and the standard deviation of the sigma of this distribution. Notice that because of our normalization, if I do the integral of px in px from minus infinity to plus infinity, I get 1 for all the time. It's always correctly normalized, as it should be. And then if I do the limit for t going to 0 of p of x, I should write pxt actually, because there is an explicit dependence on time. So let me make it explicit. Then here is the corresponds to a delta function. And is the limit of this distribution, which is a delta function. Now, this is a microscopic perspective in which we have modeled the interaction between the particles as just a sort of random process in which the position of the particle can move with one step or to the left or to the right. Okay? And we get the distribution of the position, describing the position of the particles in terms of basically this quantity here, which is the most important. So the scaling with time and the diffusion. Now, from a macroscopic point of view, instead, the same process can be described by introducing a diffusion equation. So, we can make now a macroscopic description of this system. The microscopic description of diffusion is just it's empirical, in the sense that one introducing, first of all, a density of particles, n of x, again in one-dimensional system, which is n times p of x, to this density, the total number of particles. And this, if you want, is the probability that a certain particle is in a certain position x, that a particle is in the position x. Now, the thing is that the starting point is J, which is the flux of particles, which is written as minus v times the derivative of n with respect to x in one dimension, or in p dimension is minus v gradient of n. And this is called Fick's law. And J is a flux of particles. So it's the number of particles divided by surface and time. Surface and time. Now, where does this formula come from? Well, actually, at this level is just empirical, and it corresponds to the empirical observation that if you have a gradient in the density, so suppose that you have situation in which the density has a certain profile. So here you have more particles, and here the density is smaller and smaller. Now, what you observe is that, so here you have large density, and here you have small density. What you observe empirically is that the flux, of course, there will be a flux of particles from the large density region to the small density region, and this flux of particles is proportional to the gradient, okay? So to the variation at leading order, at least, of so the gradient of the density in one dimension and 3 dimensions. This proportionality has a coefficient of proportionality which is introduced here, which is D, which is exactly the diffusion coefficient that we used before. Now, what we need to do is to impose now the conservation of the number of particles, which as usual is computed, is imposed by using a continuity equation. So this is a particle number conservation. Okay, which is a general equation that describes the conservation of a certain quantity. The gradient, the divergence of J is minus the time derivative of the density. Now we can combine these two equations, so the this one and this one, let me call it 1 and 2. So by introducing here J, I get the minus and the minus goes away, and here I have the divergence of the gradient, which is an nabla squared. Okay, so I get D nabla squared of n is equal to the derivative of n, or this is in 3 dimensions, whereas in 1D is just D second derivative of x with respect to x of n is equal to, okay, and those are 2 examples of diffusion equation in which you see that there is a second derivative with respect to x and a first derivative with respect to t, which make this process irreversible, in the sense that if you invert time, different from Klein-Gordon equation, for instance, or from a Dirac equation, in which time and x are so the derivative appears at the same level, at the same order, whereas here you have 1 derivative in time and 2 derivatives in space, and it makes this equation an irreversible equation, as we know, in the sense that diffusion is an irreversible process, in the sense that, again, we will see that particles will flow from the large density to the small density region spontaneously, whereas if we want to do the opposite, well, you need to wait a lot of time, as the calculation that we did before. Okay, so this irreversibility somehow is explicit from the fact that here we have 1 derivative with respect to time and twice with respect to space. Okay. Now the interesting thing is that now if you take the distribution that we wrote before, that was this one, P of x was 1 divided by square root of 5 for et, and here we had x squared divided by 4 dt. Well, you can just multiply by n and by hand here, and you get here the density. But n is just a proportional factor, so it's not important. Now, if you try to substitute this expression that we derived microscopically by using statistical arguments, you put in here And you see that this is a solution of the diffusion equation. So this is a solution. We actually derived also in the course of mathematical methods of physics, if you remember. We had the diffusion of heat, and we derived by using the Fourier transform this formula for the diffusion of heat. Okay, so you have two descriptions of the same process. One in terms of microscopic interaction, which is a random walk process, and the other one is an empirical description, macroscopic description, which is basically encoded in the diffusion equation. But what we get is the same. Okay? So actually, the microscopic description provides on statistical argument a solution of this equation, okay, which is macroscopic. And these are the typical games one can do in statistical mechanics. Because we have a description with respect to thermodynamics, which is more related to the microphysics. Okay, so of course the number of topics in this field is huge, and now what I think I will do is just this, the Einstein relation, and then we'll make another example of processes out of equilibrium. By the way, this kind of topics falls in what is called non-equilibrium statistical mechanics, which is, of course, another field, and we will just barely touch in these 2 hours. Now, what I will do is a sort of, it's not an exercise, but almost, is to see what happens when we have an external field. So diffusion in presence of an external field. Driving force. Now, okay, the equations that we need to remember are the ones that I already wrote. So the divergence of J is minus the derivative of N. Then we have the diffusion equation, which is d number squared of N is derivative of N with respect to T. And the Fick law, which is J is equal to minus d gradient of N. Now, suppose that we have an external driving force, F. It is a driving force. External. Which is provided by minus the gradient of a certain potential U. Okay. So it is a conservative force. Now, and let's concentrate for a moment to what happens to one single particle. One single particle. For one particle, suppose, so the situation is the following, that we are concentrating on what happens to one particle which is immersed in a system with other particles, and it also feels this potential, this external driving force. So I can write down the equation of motion in this particle, which is something we have done in the first year. So this Newton's law is minus V divided by V plus F, where V is the mobility, it's called mobility, and this P is 1 divided by M and gamma, where gamma is called friction. Which describes the motion in a viscous fluid, where the viscosity comes from the fact that this particle is interacting with all the other particles. And so there is a natural movement of this particle, which is its random walk, basically, of Brownian motion. But we have also additionally a driving force, an external driving force, which is this F. Okay, so now what we are going to derive, it's very simple, and it is a relation between the diffusion coefficient and the friction and the temperature, actually, which is called Einstein Equations. Now, what we need to do is basically, it's very simple. We have to see, first of all, what happens in equilibrium, or in stationary condition. So if I impose the stationary condition on this equation, as we call it 1, so 1 is stationary condition, I have to impose the stationary condition that the derivative of v with respect to time is equal to 0, and therefore I get that Fb is equal to v F times the mobility is equal to v velocity. Okay, this is the question. Therefore, now if I multiply by n, I get that Nb, where n is the density, is equal to Nb times F. But what is F? F is minus the gradient of u. Minus the gradient of u. So somehow this flux here is the flux associated, or the flux associated to the external external field, if you want. Okay? Flux driven by the external force or the external field. And indeed is just proportional to the gradient of u. Particles will try to move in a region where the potential is smaller. Now, so this is the flux driven by the external force, and therefore, in order to have, if you want, conservation of number of particles, I have to impose that the flux J, which is the one proportional to the gradient of the density, plus the flux driven by external force is equal to 0. Okay, of course, in equilibrium always. Okay, so now I can substitute the quantities that I know. So J was equal to minus V, the gradient of N, this quantity here, and this quantity minus N, V gradient of U must be equal to 0. Now, I use a result that I know from Maxwell-Boltzmann distribution. I know that if I have n of here, what was the variable was r, so that we are is n0, and if I have an external potential, distribution of particles or the density of particles is modulated by the potential. No, so here I will have e to the minus kBt times the potential. Okay, so this was derived in the case of the Boltzmann, Maxwell-Boltzmann distribution. So n of r scales as, okay, so n0, 0 is the position, so the density has a certain position that I take just 0 for simplicity, and then you have a modulation which is provided by the potential. Okay. So then I can now compute what is the gradient of n from this formula, because the gradient of n now is equal to this quantity, which is just n itself, times minus the gradient of u divided by kBt. So I do the gradient of this quantity, I have the same, so this factor, the exponential, which is just n, and then the gradient of u divided by kBt. Okay, so now let me put everything together. So I have here, okay, this is the gradient of n. Yeah, so now let me call this equation asterisk and put this in asterisk. So you have minus d gradient of n, which is minus and the minus goes away, so it's just dn gradient of u divided by kBt, and this one thing. Then I have minus minus. Let me just check that the signs are correct. And then this must be equal, if I put this on the other side, nb gradient of u. And the gradient of u. Then from this, since I have n gradient of u, just I derived that b, so d divided by kBt is equal to b. Or if you want, d is kBt times b, and b was the mobility, and it was 1 divided by m times the friction, m times gamma, which was the friction. Now this relation can be obtained in several ways. This is called Einstein relation. That, as you see, connects something which is macroscopic, which is the diffusion coefficient, which we introduce in our empirical description of diffusion, and something which is instead, if you want, microscopic, which is this friction, which is due to the interaction of the particles with the other particles. Okay, this is a relation that falls into the category example of fluctuation dissipation theory that we saw in other two cases, when we described the fluctuation of energy in the canonical ensemble and the fluctuation of particles in the grand canonical ensemble. In that case, we have computed that the fluctuation of energy were proportional, for instance, of the energy, it was proportional to the heat capacity. And so what is this? What was the meaning? That you have, if you have an external exchange, so an exchange of heat between your system and a source, the response of this system is provided by the heat capacity, which is a, if you want, a macroscopic quantity, which on a microscopic standpoint of view, if you want on a statistical point, from a statistical point of view, is just a fluctuation in that case of the energy of the system. Fluctuations are always present in a system, even without the presence of an external field. What those relations are describing is basically the fact that if you have an external driving force, which is, for instance, the presence of an external force, as we did in this case, the response to this external force is somehow connected with the fluctuations that the system has by itself. Okay. Well, also here there is the temperature which corrects this relation, but the meaning is basically the following: that your system, even without external agents, has some fluctuations. Is not is in thermodynamical equilibrium, but there are fluctuations as due to the fact that the system are composed by many particles, and those fluctuations are also responsible for the response to the external field. Okay, so this is somehow what is hidden in these fluctuation spatial relations. Now, the last topic, sono le 12:15, and so just tell me what you prefer. I would like to present another topic which is not very complicated, so I will do it in maybe 15 minutes, or if you want to make a break, as you prefer. Ci fermiamo e poi, come preferite, o continuo e finiamo prima. Sapete che vi prendo in giro, però se facciamo così. Okay, let's stop if you want, if you prefer. Okay, so then if I can, if I make it, I will do it. Otherwise, okay, let's stop for 5 minutes. Okay, so this was, as I said, a connection between the response of a system to an external perturbation, which is provided basically by the fluctuation that the system does itself without any external agent. This is the call of these statements. Now,
I will ask myself, this relation works only in fluid because the fluid flow is isotropic. Because I imagine that, for example, in a solid, the shouldn't be a scalar object, the diffusion coefficient.
Diffusion in that case, no, diffusion of electrons. So if you think about a metal, for instance, there could be diffusion of electrons. Indeed, there are similar calculations for the come si chiama Drude model, no, if I remember correctly from my studies, in which if you have an external, in that case, potential, electrostatic potential, for instance, and you have the motion of electrons in this fluid, you have, again, an external force, but you have the fact that electrons, there is a sort of friction which is hidden, encoded in that case, in the resistance of the material. So somehow, situation is similar. Of course, it is different for what happens to the ions which are in the lattice, so they cannot diffuse. But in principle, in that case, the external field is the electrostatic potential, and instead of friction, you have the resistance of the material. Okay, so the last topic, really the last, is again something which is beyond the thermodynamical equilibrium, and this is the process of nucleation in first order phase transition. And as I said, it's another example of a topic that can be studied in statistical mechanics, and which goes beyond the description of a system in thermodynamical equilibrium. So, okay, suppose that we take the phase diagram of water, that we saw many times, and suppose that we are an initial state here, A, and this is vapor, and here we have the liquid. And now suppose that we are decreasing, so this is pressure versus temperature, decreasing the temperature of the system in such a way to cross the first order phase transition line. Let's call it A prime state. Okay. Now, in thermodynamical equilibrium, what we know is that here we are in a thermodynamical equilibrium in a state which is the vapor, in a phase which is the vapor, whereas here we are in a phase which is the liquid. Okay, and that's it. These are the situations at the thermodynamical equilibrium. If I want to study what happens in reality when I do this transformation, although I have to take into account some more physics. Suppose that we have a box here with the phase one, which is the vapor, and phase two, suppose, is the liquid. And what we are going to describe is how we go from the vapor to liquid. Okay. Now, the thing is that when I start to do the phase transition, actually, is not that all the bulk of the material will convert immediately from vapor to liquid. There will be a process, microscopic process, which is called nucleation. What is nucleation? It's the formation of finite-sized droplets of phase 2, which is in this case the liquid, in the bulk of phase 1. So you will start to form some structures that in the simplest case are droplets of the new phase, which is the liquid phase in this case. So here, a single drop. Okay. So you have a finite volume, so with a finite size, in which you form the new phase within the bulk of the old phase. It's not that the conversion occurs immediately. You start to form some droplets, and then at some point the droplets side, well, the droplets will increase, they will merge, and at the end you will sit at the thermodynamical equilibrium in a phase which is just the liquid phase. But in the process of phase transition, there is a out of equilibrium process, which is the nucleation. Okay. Nucleation. Okay. So, for instance, if you have, so this is a case of supercooling, for instance. What is supercooling? So the fact that you cross this phase transition line and your system is actually metastable, is in a state which is still the vapor, but actually there is a small perturbation that is needed in order to make the transition. And this perturbation is provided by the formation of these droplets. Okay, this metastable state, for instance, is used if some of you are experimentalists in the cloud chamber, for instance, for detection. No? You have supersaturated gas, and then when a particle passes through, you have the formation of droplets, no, of your liquid that then trace the motion of the particle. Okay, so how do we describe this situation, which is a situation somehow a little bit out of equilibrium? We describe the situation as follows. So suppose that we take G, which is the Gibbs free energy, and let's call G1 the Gibbs free energy of phase 1, which is the vapor, G2 the free energy of phase 2, and here we have to add a term, which is this term here, that is related to the finite size of the droplets, where sigma is called surface tension. And basically, so this 4 pi r squared surface tension, of course, is an energy associated. So 4 pi r squared sigma is the energy to pay in order to form a droplet, which is a finite size structure, droplet with radius. Okay. The surface tension, as the empirical formula of nuclear physics, somehow is a price you have to pay due to the fact that you have a surface. And so those are the two energies associated with the bulk of the material. But there is an additional term which is associated with the fact that you have a finite size provided by this surface of the droplet. Yeah. Okay, so now what do we need to do is basically just to minimize the free energy, and the game is almost done. So let's compute first of all the variation of the Gibbs free energy. Sorry, and I will comment in a moment why we are considering the Gibbs free energy. dg, so the variation of Gibbs free energy, is equal to dg1, but dg1 is mu1 dn1 plus mu2 dn2. Then we have, we have a 4, 8 R sigma phi plus 8 phi R sigma dr. Okay. And why I'm considering GIPS? Because we are working at fixed pressure and fixed temperature. So we are, well, we have decreased already the temperature, and we are sitting at the point that I called A prime, in which now the pressure and the temperature are fixed, and then we want to see what happens to our system. The potential, the right potential to take to consider is the Gibbs potential, because the second principle of thermodynamics tells me that the Gibbs potential is minimized in situation in which the pressure and the temperature are fixed. Okay. So second law tells me that I have to minimize G, where when fixed P. Okay, now to do this calculation, first of all, let's write down this equation, which is the conservation of the number of particles. dn1 plus dn2 is equal to 0, from which dn1 is equal to minus dn2. And now dn2 is positive since we are moving, so we are so some particles from phase 1 are going to phase 2, no? So from 1 we are going to 2. So then let's write dg as by collecting dn2, I get dn2 times mu2 minus mu1. Then we have this additional term, which is 8 pi r sigma and pr. Now this can be also written in terms of dn2 by using this relation. Suppose that n2 is the density of phase 2, and this will be n2 number of particles, n2, divided by the volume occupied by phase 2, which is the volume of a droplet. So 4 pi r cubed. Okay. Now from here, I can basically write that so n2 is equal to 4 pi r cubed n2, and dn2 is equal to, I have to derive this, so I get 4 pi r squared n2 r, from which dr is equal to dn2 divided by 4 pi r squared n2. Okay. So if I have done my calculation properly, now this dr instead is dn2, and here I have 4 pi r squared n2. And now dg can be written in this form. So dg is equal to dn2, which can be collected. Then we have mu2 minus mu1, and then we have 2 sigma n2r plus 2 sigma r. that's correct. Now, from the second principle of thermodynamics, this must be smaller than 0 from second law. And therefore, we conclude that mu1 minus, or mu2 minus mu1 plus 2 sigma r and 2 must be smaller or equal than 0. Which also means that mu2 is less than mu1 plus 2 sigma r and 2. Now, this is a positive number because sigma is a positive number and r and 2 are positive. Therefore, this condition is telling me that in order to have nucleation and therefore to start my phase transition, mu2, so the chemical potential of the new phase must be strictly smaller, if you want, than mu1, which is the chemical potential of the old phase. Okay, so this is the condition to start the phase transition. So the fact that we have this formation of finite size structures somehow imposes that the chemical potential of the new phase is smaller than the chemical potential of the old phase. Of course, when the phase transition will be, so if we are instead in a situation in which phase 1 and phase 2 are in equilibrium, for instance, I am in the mixed phase, so in mixed phase, but I think, of course, we said that mu1 is equal to mu2 because of thermodynamical equilibrium, and we need to have chemical, there's no chemical imbalance, okay? But if I want to start the phase transition, I have this condition. So the chemical potential of the new phase must be smaller than the chemical potential of the old phase. And then at equilibrium, for instance, if I form a mixed phase, these two chemical potentials must be equal. Okay? Now, the last consideration that I want to do is the following. So that's the reason for which we have metastable phases, because we have somehow to go a little bit beyond what is the chemical equilibrium condition in order to start with the phase transition, and then we have the occurrence of the formation of, so the formation of droplets, the merging of droplets, etc. Okay. But at the beginning, I have to consider a system which is out of chemical equilibrium, so out of thermodynamical equilibrium. Now, indeed, let's define, so we said before that mu2 minus mu1 plus 2 sigma n2r, this must be less than 0, is what we wrote before. Let's define a critical value of the droplets. So the critical value of the radius of the droplets. Let's define r crit by using this equation with equal to 0. So r crit is mu1 minus mu2. So this 2 sigma sorry, portare questo di là, mu2, so mu1 minus mu2 is equal to 2 sigma divided by n2r, and for n2 divided by 2 sigma and mu1 minus mu2. The opposite. So is 2 sigma divided by n2 and times mu1 minus mu2. So these critical conditions that is obtained from the minimization of the Gibbs free energy with the equal here instead of minus provides me a critical radius for which something will happen now, because I can give an interpretation of this arcrit. Indeed, what happens in the system is that when we have crossed the first order phase transition line, by fluctuation, just because of fluctuation, again, fluctuation, I can form droplets of phase 2 with different sizes. Okay. Now, if I form a droplets, if I form, not me, but if the system forms a droplet with R smaller than this critical radius, okay? So that means that R is smaller than what is the critical radius, 2 sigma divided by n2 times mu1 minus mu2, from which I can obtain that mu1 minus mu2 is smaller than 2 sigma and 2r, smaller than 2 sigma divided by r and 2. Okay, but of course, if I call this equation asterisk, the equation asterisk is telling me that mu1 must be larger than mu2 in order to minimize the Gibbs free energy, whereas here I'm saying that mu1 is smaller, strictly smaller than mu2, because mu1 is smaller than 2 sigma plus mu2. Okay, so actually this condition violates this condition here, just because I have a minus, if you want. Okay. So mu1 minus mu2 violates 1. Asterisk. Sigma, because I can put, if you want, I can put this mu2 there minus mu1, and I see that 2 sigma r and 2 mu2 minus mu1 is larger than 0, whereas here it should be smaller than 0. So it violates asterisk, so it violates the second principle of thermodynamics, and therefore for this kind of droplets, basically they will disappear. So that means that qua, so droplets with are smaller than this critical radius will disappear. Because they are not convenient from the second principle thermodynamic point of view. So this will disappear because it violates second principle. So they are not helping, if you want, in reaching the thermodynamical equilibrium, which is the second principle of thermodynamics. Whereas if droplets, if the fluctuations are responsible for the formation of droplets which are larger than this critical radius, then this droplet will increase, will get larger, and the phase condition occur. Okay. So it's again a matter of fluctuations. There are fluctuations producing small droplets, fluctuations that produce large droplets. The small ones will just disappear because they are not helping reaching the thermodynamical equilibrium, whereas the large ones, they will increase because they are favoring the thermodynamical equilibrium. Okay? So, and this is what happens actually when going beyond the thermodynamical description. Okay, so with this, actually, I finished 10 minutes before. Yes.
Sorry. I have a question. Can we make an analogy with the phase transitions we saw in IT models? So these droplets, the clusters of magnetic moments that move. So there is nucleation also.
No, yeah, in principle there is such a process because these are general feature of first order phase transition. So the fact that you have first order phase transition is characterized by the fact that they are forming finite size structure. So also in that case there is something similar, though we have not introduced a quantity that somehow encodes this formation of finite structure, which is the sigma. Okay. So in that case, below the critical temperature, yeah, so something similar to this, in the sense you have the formation of finite size clusters of aligned magnetic dipoles, whereas at the critical point instead, so at TC, exactly at TC, this is a second order phase transition, and there is no typical scale. So here the scale somehow is provided by the sigma, but in a second order, which is the fact that we have studied more in that case, there is no typical scale for the size of the clusters, and this because of the fact that the correlation length explodes, as we said last time. Okay, but below TC, something like this will happen because it's a first order phase transition. Mm-hmm. There are other questions about the physics or about the exams or the organization of the exams. Just tell me. So, in principle, we can start by the second week of. Let me see. Vediamo il calendario. Direi dal 14 in poi. So, from the second week of June, we can start with the exams. And I think I sent, ma posso parlare in italiano forse? So parlo in italiano. Ci sono solo due. Siamo io e un altro. Ok, parlo in italiano. Per l'esame, se riuscite a clusterizzarvi in 5, se riuscite. Così facciamo uno scrittino breve, ma piccolo proprio, e ne facciamo 5 al giorno. Quindi se riuscite a organizzarvi in modo da venire 4-5 alla volta, resta un piacere. Poi io, visto che siete pochi, ma anche nell'altro corso in realtà non fisso un appello, cioè quando siete pronti me lo dite, vi organizzate tra di voi e facciamo l'appello. E mi raccomando, compilate le schede di valutazione dei corsi, perché così se ci sono, diciamo, in particolare commenti su come migliorare, ovviamente sono ben accetti, ok? Perché questo è il secondo anno che faccio questo corso, quindi sicuramente ci sono delle cose da sistemare e da migliorare. Bene, vi saluto, voi da casa.
Arrivederci, buona giornata.